I do need to show you some code, and I know that people talking about code on YouTube is just mind-bogglingly dull, but there are a couple of bits that are important, and one of them is this, which is a union. When I'm reading data in from Daniel Collins's I2S data buffer, I'm reading in 32-bit signed integers, but in order to do maths on them, I'm converting them into floats. But I'm converting them into floats, which are just stored in 4 8-bit words, i.e. in a 32-bit word. I'm storing them in a union, and a union is something in C, which is really quite neat, because it means that multiple data types can occupy the same space in memory. So I can store my floating point sample in the union, but I can access it as if it was a 32-bit integer. And this is important because Ian Scott's code for reading and writing to SPI memory needs 32-bit integers, but in order to do maths on the samples themselves, I need them as floats. But a float is a 32-bit word, and so by storing it in a union, I can either access it as a float for doing maths on it, or I can access it as a 32-bit signed integer if I'm storing it in memory or reading and writing from memory. This is where I'm processing the input buffers from Daniel Collins's I2S code. So I'm just at the moment processing the left channel. I'm not processing the right channel, just to make it a bit easier for myself. But this is where the unions are coming in. So I'm reading from the input buffer, that's a 32-bit signed integer, and I'm casting it as a float and storing it in the float part of the union, a union called this sample. And I'm taking a copy of that in something that I'm calling dry sample, because I'll need that later. And then I am reading from the read pointer, and remember, this is something that will have been written a little while ago, so I'm reading a 32-bit integer into the read sample. So the 32-bit integer data type within the union called read sample. And then what I'm doing is taking what's just been recorded, what's just arrived, and I'm adding a small amount of what I've just read from memory. So this read sample is something that happened a while ago. I'm multiplying it by a feedback constant, something between 0 and 1. So I'm adding a little bit of what happened a little while ago back into what's just arrived just now. And then I'm going to write that to the right pointer position, which is writing to the here and now position in the buffer. And then finally, what I'm going to return is a mixture between the dry sample, remember that's what arrived up here, so it's what's just arrived without being monkeyed with, and the read sample, so that's what's come from memory written some time ago. And I've got a little function that mixes those two together and returns them and pokes it into the output buffer. And then finally I'm just wrapping the read and write pointers at the end of the buffer. Here we are again. I've added 3 potentiometers that I've connected to the analog to digital converter inputs. And first of all, there's a horrendous crackling, and we need to talk about the crackling. I think it's data errors on the ADC input. If I put a capacitor across the input here, that's across the 5-volt line, and ordinarily you'd expect that to smooth the line out, but it makes it far worse. So I think I've got noise, and we're going to have to do something about that. And it's probably that I'm trying to run high-speed audio on a breadboard, and breadboards are horrendous when it comes to you know, decent ground planes or anything like that. But anyway, I've got these three potentiometers. I haven't really decided what I'm going to do with them all yet, but this one is the feedback amount, and this one I've got wired up to an in-out balance. And actually I can't hear that through all the row, but if I turn the feedback up and turn the wet-dry balance up, I've got control over the amount of feedback and the balance between the wet and dry signals, but I'm going to have to do something about that noise because it's horrendous. I thought I'd have a look at the PCM1808 and noise and see if you know, what I have to do about it in terms of circuit design in order to eliminate it. And if you search for PCM1808, look, you find loads of these. They're little pre-built modules available from various places, eBay, AliExpress, and so I thought I'd have a look at these. I'm on AliExpress, well-known souk from the Far East, and they're selling these modules for £1.19 plus shipping, obviously, but just to buy the PCM1808 chip alone in small quantities from somewhere like Mouser is going to cost me more than that. And having a quick look at this circuit, or this little module, it looks to me like they've pretty much followed exactly the layout example from the Texas Instruments datasheet, that you've got some input capacitors, DC blocking capacitors, you've got what appears to be a low pass and anti-aliasing filter, you've got the chip itself, and you've got some other smoothing capacitors, you've got millions of vias between ground planes on top and bottom, and they've done a really nice, neat little job of laying it out. And I can buy these cheaper than I can buy the chips. So I'm thinking. Then I searched for PCM5102, and you can get similar little modules that include these. Now this is interesting. If you recall, when I looked at the application circuit in the Texas Instruments datasheet, I remarked that there were separate 3.3 volt rails. Now it looks to me as if these are little 3 volt regulators. So it looks like this module contains all of these components ready assembled for 1 1/3 of our English pounds. So, you know, I'm questioning why I should buy the chips and go through the effort of making up a circuit board with all the ancillary components when I can just buy one of these and solder it in. And because I'm impatient, both are available via other well-known online souks with next day delivery, so I'm going to pay a little more and get myself a couple of these to play with.